Okay, so here's the second part of the lesson. We're going to talk a little bit about how light and space interact and how we can figure out stuff around space because of light. So first thing to talk about is light is kind of similar to sound in that it's a wave. It's an electromagnetic radiation wave, but it's still a wave. So a lot of the things that we think about when we think of sound waves, we can also apply to light waves, which you're going to find out a little bit later. But just remember throughout this that light is a wave. So let's talk a little bit about the electromagnetic spectrum. This is something that hopefully you learned some about in grade 8. EMR includes all electromagnetic radiation that travels at the speed of light, so that 300,000 kilometers per second. There are different forms of electromagnetic radiation, and they vary in wavelength and energy and frequency. So as we have higher frequency, that means they have shorter wavelength, and as a result, more energy. So for example, gamma rays right here have very tiny wavelengths, and as a result, they're very high energy and very high frequency. While as we go to things like radio waves, they have very long wavelengths, and as a result, they are lower energy and lower frequency. Visible light is right here, so it's kind of right in the middle of the spectrum, and that's what we can see with our eyes. But there's other electromagnetic radiation that we can't see with our eyes, but that can still tell us stuff about celestial bodies. So to begin with, Isaac Newton discovered that when he put light through a prism, that it produced a spectrum of colors. It separated into all of these different colors when he put white light through. And this is super useful because we can actually tell things by the colors that are missing. So by using something called a spectroscope, which is a device that produces fine, detailed spectrum of colors after light has passed through a narrow slit, we can see different colors and figure out what we have present and what we have missing, and that can tell us stuff about the composition of celestial bodies. So a spectroscope basically has something called a diffraction gradient or diffraction grating, which is really close together lines. And as light travels through it, it causes light to split into this spectrum. So two Germans, Kirchhoff and Bunsen, played around with different types of spectroscopes and found that there are 3 types of spectra that you can produce. One is a bright light spectra or spectrum, a continuous spectrum, and then an absorption or dark line spectrum. So here's kind of what these look like. So a continuous spectrum means that it's just the full rainbow. We don't see anything here in terms of gaps. When we have a bright line or emission spectrum, we have only bright bands showing up. So this happens when we excite a gas, like we put electricity through a gas, and we end up having this. And then we have absorption spectrum, which talks about what light is absorbed by the black gaps. So wherever there's a black gap that occurs on the spectrum, that means that that particular frequency of light has been absorbed by something, which is why it's not showing up here. So if we look at, let's say, the sun, we're going to see these dark lines of the spectrum from the sun because the sun's atmosphere, what it's made of, has absorbed those frequencies of light, so they do not show up. We also call this a dark line spectrum as well. And that's what we're going to be looking at mostly today, almost entirely. So we have continuous spectrum, the full spectrum again, emission spectrum, which again, or bright line spectrum, which shows the bands as bright lines when we excite a gas, and then finally absorption spectrum, which shows the dark bands where light has been absorbed by different elements. Okay, we're going to skip a few slides here because we want to talk about how that shows up. So what diffracting gradient is, or grating, is a series of closely spaced slits that cause the light to bend, diffract, and produce more detailed spectrum. And that's what we rely on in the spectroscope, is diffracting or diffraction gradient or grating. Just different terms, same thing. So star spectroscopy. Knowing the spectral absorption for each element, scientists look at the stars and compare the lines to determine the composition of stars. So we can actually take a look at stars with the spectroscope and figure out what those stars are made of by the dark line spectrum or spectra that they produce. So here's how this works. This is essentially the dark line or absorption spectrum for different elements. So hydrogen, helium, sodium, calcium, and mercury. And these are the elements that we're going to be dealing with in this example. You will always be provided with the dark line spectrum for different elements. It's not like you have to memorize these patterns. That would be super hard. But what you do need to do is match up these to the different stars and figure out what they're made of. So typically what I do is I actually work through and figure out what band lines up but doesn't line up for any other element. So for example, I can see that this band for helium lines up really well with this band in the sun. So given that that's occurring, I know that I have helium present. So right here, this matches up with this. So I know I've got helium. And then for hydrogen, I can see that this matches up right here. So I've got hydrogen and I've got helium. This band matches up with helium again, as does this band right here. But these two bands don't match up with either hydrogen or helium, so I have to have something else, and that matches with sodium. So in the sun, I know that I have hydrogen, I have helium, and I have sodium. Now let's put the element symbol there. Okay, what about Mystery Star 1? What does it have? So Mystery Star 1, I can see a hydrogen peak right here as well as here. So that matches up with hydrogen, and this one does as well. And then the other thing that I see seems to match up with calcium because I have this band, this band, this band, this band, and this band. So all of these match up with the calcium absorption spectrum. So this would contain hydrogen and also calcium. Okay, what about Mystery Star 2? So Mystery Star 2, I can see again a hydrogen peak, right? So this corresponds to hydrogen, and that's also going to give us this peak and this peak. And then I have this line right here, which fits in very well with helium. So that's my helium line. This is a helium line as well. Again, helium, and this is helium. So the only two elements I have in Mystery Star 2 is hydrogen and helium. Okay, finally, the most complicated, Mystery Star 3. So I have this line, which actually lines up with Mercury. So I'm going to go ahead and put Hg down for Mercury. And then I have that hydrogen line happening again. This line shows as helium, right? Helium right there. So He. And then again, I've got, my Mercury line, what does that line up with? Calcium? Do I also have calcium here? Crazy. This is hydrogen, this is helium, this is calcium. Okay, this line right here is again corresponding to Mercury. I've got calcium. And I'm doing extra work here. Okay, I don't have to label each one of these lines. I just have to identify what's inside of it. Then I've got a Mercury line here again. These two lines are matching up with sodium. Okay, because I've got sodium here. Then I've got helium again. This line matches up with calcium, calcium. This line is hydrogen, and this final line is helium. So I got everything here. I've got hydrogen, I've got helium in there as well, right? As I can tell from the helium bands. I have sodium because I have those two sodium lines that are held in there. Okay. I've got calcium happening as well. I've got mercury happening. I have some mercury bands, so I have every single one of these elements in here, which is just kind of crazy. So that's Mystery Star 3. Hopefully that makes sense how those work. So we know that sounds move in waves, and so does light. Sound changes pitch when moving towards or away from an object. We call this the Doppler effect, right? So that sound of meow as something goes past you, that's the Doppler effect as it goes from higher frequency, that to lower frequency as it goes past. And that happens with light as well because it's also a wave. So light actually will change color based on how things are moving when they're moving at incredibly high speeds. So if a star is coming towards you, it's getting brighter and more blue. You can think about this as if something comes towards you like a fist, boom, it punches you in the eye and gives you a blue eye, black and blue eye, right? So coming towards you, blue. If it's going away, it's red shifted. So blue shifted is coming towards you, red shifted is going away. So what that means is the star will appear more blue or more red based on its movement. So that's kind of the idea of the Doppler effect and how things actually change. So we can actually tell how fast a star is moving based on which way things are shifted because of the Doppler effect. So this kind of shows you that idea. You can see that I have the same absorption spectrum here, right? So if this is the normal one, let's say this is the normal one, and it shifted to this, it shifted more towards the red, right? So this band right here corresponds to this band right here, which has been shifted more towards the red part of the spectrum. So this star is moving away. Well, here, this is the same band, right? There and there. So this is more blue shifted, so this is moving towards from the observation point. So that's the idea, is you can take a look at these absorption spectrums and figure out then what direction it is moving by knowing which way it shifted. You're not going to have to do much of this, just understand the idea of how the Doppler effect works. Yeah, so basically this is just what we've already covered before. It's somewhat a redundant slide, so we're going to move on. All right. This we are not going to do. We're going to talk about triangulation. We can tell where things are in space by trying to triangulate them from using our different views. The beauty of Earth is that it's in an orbit around the sun. So if we take a look at objects half a year apart, then we have these two very distant points that we can use to triangulate how far away something is based on the angle. So if we know this angle and this angle, then we can actually figure out how far away something is. So the idea is if I have this and I know the baseline and I have one side and two angles, then I can figure out this distance using a little bit of trigonometry. You're not going to have to do the math on this. You just have to understand the idea of how triangulation works, that if we have the baseline and we have two angles, we can triangulate how far away something is. So if we were in school and going outside, we could actually do this by measuring the angle towards a common point and then measuring the baseline and another angle, and then we can use some trig, some right angle trigonometry to figure out how far away this object is from this point on the baseline. Anyways, this is all done because of the idea of parallax. So we talked about parallax at the very start of this unit. The idea of when you close one eye and then the other eye, you actually see a difference in position, a shift in position. And that's because your two eyes are that kind of baseline apart. They're that far apart. So as a result, this is triangulation works on the idea of parallax. It's the apparent shift in position of a nearby object when the object is viewed from two different places. So we can use a star's parallax to determine what angles to use when they triangulate the star's distance from the Earth. And by using those two angles, we can basically figure out how far away that object is. So if we take a look at the position, let me bring this to the front. In January versus June, half a year apart, then we can figure out how far away something is by knowing the orbit of the Earth and how far it is from here to here. So it's the baseline, and that allows us to find the location or distance for very far away things. Here's another diagram showing us the exact same thing. All right, let's talk a little bit about rockets and then space travel. The science behind rockets began 2,400 years ago when Archimedes boiled steam in a porcelain pigeon. The first rocket using rocket or liquid rocket fuel was made in 1926 by Dr. Robert Goddard. You don't have to know any of this or the dates, it's fine. Nowadays we use liquid rocket fuel, and the reason why is because it burns incredibly hot. Normally we use hydrogen and oxygen, liquid hydrogen and liquid oxygen, and it just makes water when it reacts, but releases an incredible amount of heat and gives a lot of thrust in that reaction. This all works under the principle of Newton's third law, that for every action, there's an equal and opposite reaction. So when I push on my desk, on my rolly chair with my feet up, I push this way, I move back. That's Newton's third law. I push there, I move this. So when the rocket pushes by having combustion happening at the back of it, pushes down, then that results in the rocket going up. And that's Newton's third law, and that's the principle behind all rockets. It's the same principle as blowing up a balloon and then releasing it, and that results in, of course, it blowing up or away or whatever. Ancient rockets used solid rocket fuels like gunpowder, but modern rockets now we're dealing with that liquid rocket fuel instead, which provides more thrust. The thing that the rocket carries is called the payload. Okay, so the payload is what it's actually carrying, what is meant to get up into space. In the past, when rockets were just kind of missiles or whatever, the payload was an explosive, but modern rockets can carry things like satellites, explosives, people as their payloads, like for example, people going to the International Space Station. Rockets, in order for them to actually get into space and escape Earth's atmosphere, have to reach 29,000 kilometers per hour. So they have to go pretty fast in order to get out of Earth's gravitational pull. And it's tough. So often multi-stage rockets are used to propel the rocket through the atmosphere. And then once that fuel is gone, there's no point in keeping that part of the rocket because it's now had the fuel used up. So it's better for it to be left or for it to lose that stage of the rocket so that the rocket becomes lighter. So this results in multi-stage rockets, which means that once fuel is used up for a fuel canister, it drops that to reduce the weight and increase the space fuel economy. So a stage is a section of a rocket that drops off once its fuel is used up. In the past, stages would just end up in the ocean, but now when you're looking at SpaceX and stuff, they're actually managing to land those stages afterwards, which is really neat, so they can be reused. Quite amazing. Because there is easy access, or there is not easy access to fuel in space, other sources of fuel are needed to be used. So future space rockets or probes need to use cheaper fuel sources. Ion drives use xenon gas rather than liquid fuels and only produce a small thrust, but only need 1/10 of the fuel in order to operate. So ion drives can be possibly used in space. Another option is solar sails, which use light waves to propel it in space. So by collecting light waves, it actually allows it to move around. Just like sails on a sailboat collect wind in order to move around as well. All right, moving forward, people in space. The Soviet Union's Vostok 1 was the first spaceship to actually put a person into space, but Apollo 11 was the first spaceship to land on the moon. This is the International Space Station, which is still obviously orbiting around the Earth and does valuable space research. People go up to the International Space Station and spend months there at a time, astronauts, in order to do studies and work on things around space. New modules are added over time. Really neat thing to learn about the ISS. So Canada's contribution to kind of space stuff is the Canadarm. Canadarm1 went to work at the International Space Station in 1981, and then Canadarm2 joined the ISS in 2001 and has kind of a new robotic hand. Dexter, the newest robotic hand for the Canadarm2, was launched May 11th, 2008. So keep on adding to it, and very useful for doing things on the International Space Station. So, dangers in space that they need to think about when going into space. There's a lot of things. Basically, there's tons of stuff that has to be thought about in terms of people staying safe on space, like radiation, the extreme temperatures, how do you get oxygen, how do you get rid of the carbon dioxide, how do they get water, and there's systems to deal with all of these different concerns. And they're going to be in your notes, but there's many different things that have to be worried about, and they're all actually settled by different systems that are on the spacecraft. So for example, when it comes to water, this sounds disgusting, but all of the water gets recaptured when it comes to like water in waste and stuff. So when astronauts pee, it actually goes through filtration, and they end up drinking that water again afterwards after it's gone through a full filtration process. Also waste just kind of gets discarded. like solid waste, that sort of thing. The water that they let out when they breathe gets collected as well and filtered and used again. So it's a closed system where everything gets reused. Oxygen can be made by splitting apart water into hydrogen and oxygen, that sort of thing. Another thing astronauts need to be careful of is microgravity. Although there is gravity outside of the atmosphere or in the atmosphere where the International Space Station is or space shuttles are, the International Space Station is in constant free fall. So it's falling towards the Earth, but because it's moving forward and never gets any closer. So if this is a diagram, wait for it, of the Earth, right? And here's the ISS. It's constantly falling towards the Earth because of the gravity, but because it's moving forward as well, it never actually gets any closer. So it just kind of keeps on going, you know, around in a circle, because as it's going, it keeps on falling. So as a result, its orbit just kind of stays in the same spot around Earth. I don't know if that makes sense. So if you want to feel like an astronaut, if you're ever in an elevator and it falls, well, at that point, you feel like an astronaut, because really, astronauts and the space station and everything is in free fall, but it's never getting any closer to the Earth because it's always moving forward as well. There's problems with microgravity. Like, for example, with microgravity, bone density starts going down because there's no shock or force on the bones. So the bones stop being as strong. The heart doesn't have to pump as much, right? Because there's no gravity it's fighting. So the heart gets weaker over time. There's a lot of different issues, and it's something that they try to prevent or help during time at the International Space Station with things like space travel and stuff. So the International Space Station allows us to study the long-term side effects of microgravity, such as the weakening of bones. Anemia can happen, which is the loss of blood cells to provide oxygen to the body, and blocked sinuses, like an allergy, because there's no gravity pulling it out, so they have to use suction instead. This is a little bit about all the different systems that are on the International Space Station or any spacecraft, things that they have to worry about, like, for example, how do you get oxygen? Well, by getting water and generating oxygen from splitting it apart. We have urine recovery, which gets processed to make potable water, so water that can be drunk, which is used for showering and hand washing and other ways, and then that gets processed again. There's waste management. Everybody poops, including astronauts, so how do we get rid of that? Temperature and humidity control, air, all sorts of things to worry about. So there's many systems on spacecraft. It provides a really interesting engineering challenge, and amazing that they can make it work to kind of have essentially a closed system, not isolated. There's still energy getting in from the sun and so on, but a closed system that works in order to have people live there long term, or at least months. Also, on the spacesuit itself, astronaut suit, you have tons of things that help with different space dangers, like liquid cooling and ventilation, drink bag for drinking. You have actually diapers. They don't talk about that, but you still got to pee even when you're in the space suit. So you have maximum absorptive devices, upper and lower torso assembly, lots of things, batteries to power everything that needs to be powered, battery packs, life support system, all sorts of stuff. Really neat. So essentially, when you have a spacesuit, an astronaut suit, it's almost like a miniature spacecraft going on a small scale. All right, last thing here, just kind of the political, ethical, and environmental issues. As we kind of deal more and more with space travel, we deal with more things like space junk, who owns different things in space, who owns like the area of space above us, that sort of thing. So it creates a lot of issues, and more space is getting crowded around the Earth as more satellites are linked up, and more space junk is around. We saw recently that satellite falling, and there's a lot of kind of like buzz around that of where is it going to fall, because they just didn't know. And these are issues that are kind of coming to light as we're leaving stuff into space and treating it as tomorrow's problem. So something to think about. It's interesting. All right. Well, that's it. That's it for space. That's it for this lesson. Have a good rest of your day.